Now, what is an equipotential surface? An equipotential surface is a surface where all points on the surface have same potential. Now, suppose you have a point charge q and potential at a distance r is equal to v equal to kq by small r. Now, which surface is having this potential kq by small r? Obviously, it's a sphere. All points on the sphere has this potential. So, this is an equipotential. The sphere of radius r is an equipotential surface having potential this much. Also, you have so many concentric spheres. All the concentric spheres are equipotential, having the center at the charge q. Now, what is the relation between the electric field and the equipotential surface? Now, suppose you consider a two-dimensional diagram of the surface. This is on the surface, and say this is point A and point B, very close points on the surface, so that the distance, this is only delta r, denoted by the vector. Points 1 and 2 are very close to the surface. And suppose the electric field vector on the surface is E, making an angle theta. Now, we know this A and B are two close points on equipotential surface. Okay, so VA minus VB equal to how much? E say E dot delta R, right? So VA minus VB equal to E into delta R into cos theta. Now this VA minus VB is equal to 0. VA equal to VB, so that means E delta R cos theta is equal to 0, implies, see, neither E is 0 nor delta R is 0. So therefore cos theta equal to 0, that is theta equal to 90 degree. So therefore the electric field vector is always perpendicular to the equipotential surface. We can conclude that. So electric field or electric field lines, we will discuss that in a later video. What are lines? That means the electric field lines or the electric field vector perpendicular to equipotential surface. Okay. So suppose in a region you have uniform electric field, a region having uniform electric field. Where does this situation happen? You know, it is the field due to infinitely charged plate. However, these are the electric field lines. Now, which are the equipotential surfaces? You know, these parallel planes are the equipotential surface. If you are not convinced, then I can help you out with this three-dimensional diagram of equipotential surface. See, these are, I mean, imaginary surfaces, na? You can't catch hold of the surface. So let me draw the field. The field will pierce through the surface like this. Like that. there it is, piercing through the equipotential surfaces. Suppose this surface, suppose this potential throughout this surface is, it happens to be 20 volt, and this surface happens to be 10 volt, and this surface happens to be 0 volt. And let us see about the distances between the surfaces. Say these all distances, say equidistant. Suppose this and this both are equal. Suppose this happens to be 2 meter, and this also happens to be 2 meter. Uniform electric field. So what is the value of the field? What is the magnitude of the field here? So from this, you know, the field is equal to how much? 20 minus 10 by 2. So here in this diagram, say it is 20 volt, 10 volt, 0 volt, and this is 2 meter, this is also 2 meter. So E equal to 20 minus 10 by 2, that is 5 volt per meter or 5 Newton per coulomb, whatever. So you can have equipotential surfaces like this, say xy plane, say this makes angle theta. These are the equipotential surfaces, and the potentials are, suppose say this is 10 volt, this happens to be 20 volt, this happens to be 30 volt, and all these angles are theta. And suppose these all gaps happen to be a each. Now these, I mean, the equipotential surfaces are the planes perpendicular to xy plane, right. So how are the electric lines of force? They will be perpendicular to the equipotential surfaces. So it is. There it is, and see the direction of the field is from high potential to low potential. So this is, how much is this distance? That's a, so that's a sine theta, right. This much distance is a sine theta. So the field, uniform electric field, obviously, else the equipotential surface would not have been planes. So equal to that 20 minus 10 divided by this distance a sine theta, whatever it is, the values will be given volt per meter or Newton per coulomb. This is how you calculate. Right. Now say, suppose this is a ring, the charge ring, charge q, radius r, at a point P. What is the potential at a point P? At point P on the axis of the ring, the potential is equal to, so for calculating potential, consider these dq charges. Now it is equidistant, right. So this distance is root over r square plus x square. So it is integration of k dq by root over of r square plus x square. In this integration, only this dq will sum up to give q, kq by root over of r square plus x square, and the field is equal to minus dv dx, because you have to calculate field here, and this field, this field varies with x only on the axis. So minus dv by dx means minus of k dq by this will be 2 r square plus square to the power minus 3 by 2 times 2x. Now you have a minus half here, so it will be plus. So equal to kq x by r square plus x squared to the power 3 by 2. And we have also calculated the field at this position just to verify it.